2.3 exponential functions.
In math, we study several different types of functions. 3 types of functions seem to keep showing up in every math course from Algebra 1 to Calculus. These 3 families of functions are also featured predominantly on the SAT and ACT.
All right, so a linear function has a degree of what? What's the degree of a linear function? 1. All right, beautiful. And a quadratic function has a degree of what? 2. An exponential function, what makes it exponential? The what? The variables in the exponent. All right, beautiful. Keep going, Lucas.
Exponential functions are some of the most important functions in the real world. They appear in many places, including population growth, money, interest and debt, radioactive decay, spread of disease, etc. In addition, the SAT will include several questions that require an understanding of exponential functions.
All right, so an exponential function, we're going to be talking about this form of a times b to the x. All right, and so we need to talk about those, and if you understand what a and b do, this lesson is not going to be hard. However, if you don't understand what a and b do, this lesson is going to be extremely difficult. So let's talk about what they mean. So a represents the initial amount. All right, it is how much you start with. So a is your initial amount, and b is your base or your common ratio. I'm mostly going to refer to it as the base. All right. And so just like we did with geometric sequences, exponential functions model a geometric sequence. However, it's a function, so it's connected. But if you understand the base and initial amounts, we should be pretty good to go on these. All right. And so let's look at these graphs. So if I have an exponential function, when a is greater than 0 and b is greater than 1, it's going to be a growth like this. All right. And this is the way I kind of think about it. If you do 2 times 2, what do you get? 4. So you get something larger than what you started with 2. Does everybody follow me? So 2 times 2 is 4. 4 is bigger than 2. It grew. Okay? And then if you look at exponential decay, and so if a is greater than 0 still, all right, so my initial amount is still positive, and then b is in between 0 and 1. And the reason why it has to be in between 0 and 1 is because if it's negative, it actually flips. Remember that? So if it's negative, it's going to flip. It's going to reflect over an axis. So it has to be between 0 and 1. And so this is the way I think about decay. So think about like something between 0 and 1, like 1/2. Well, what's 1/2 times 1/2? 1/4. Well, which one's bigger? 1/2. So it got smaller. Is everybody following me on this? So now that's a decay. All right, and we're still going to talk about increasing and decreasing. And so exponential functions are always increasing or decreasing. They have no relative extrema. And so what is this one doing? An exponential growth is doing what? It's increasing. An exponential decay is what? Decreasing. All right, and we're going to talk about concavities as we go along. And so concavity is either concave up or concave down. And so on this one, it's what? Concave up. This one is also what? Concave up. All right. So when do you get concave down? When it reflects over the what? The x-axis. So for instance, if I end up saying like, hey, a is less than 0 and b is greater than 1. B is greater than 1, silly goose. B is greater than 1. What does that do? It reflects over the what axis? The x-axis. So now it's looking like that. And so if a is less than 0 and b is greater than 1, it's going to reflect like that, which means it has a what kind of function? Is it increasing or decreasing? Decreasing, and it's concave what? Down. And the same thing happens over here. And so if your a is less than 0 and your b is in between 0 and 1, what is that one going to look like? It's going to reflect over what again? The x-axis. And so now it's going to look like that. And so would that be an increasing or decreasing function? It's an increasing function. However, it's also what? Concave down. All right. Do we see how that worked? All right, cool. And so now let's talk about in behavior. And in behavior is with limit statements. So a limit to infinity or negative infinity. And it's either going to be infinity, negative infinity, or 0, depending on which way it's going. All right. All right, so example 1, we're going to write limit statements for in behavior for these exponentials. So how do we write a left-hand limit statement? A limit as x approaches what? negative infinity. Exactly. Now, do we know what this function's called? Does it have a name? No, it doesn't have a name, so we're just going to call it ab to the x because we don't really know what it is. All right, and so when I go left, what's it leveling off to? What's it going to? 0. It's leveling off to 0. And then how do I write a right-hand limit statement? A limit as x approaches what? Positive infinity. And does it have a name? No, so I'm just going to call it ab to the x. And so what's it going to there? Positive infinity. Exactly. All right. Now, I want to break this one down a little bit more. What is a? Is a positive or negative? On this one right here that I'm working with on a.
Positive.
A is positive. And what is b? Is it in between 0 and 1, or is it greater than 1? What made it do that? It's greater than 1 because it's an exponential growth. All right, let's look at b now. Let's look at b. This one's a little bit tricky, but we're going to do the left-hand and right-hand limit statements first. So to do a left-hand limit statement, we do a limit as x approaches negative infinity. Now, does this one have a name? No, we're going to name it, and we're going to name it after Kefa, so it's going to be called k of x. All right, we're going to name it k of x. All right, and so now we're going to have k of x as x approaches negative infinity. And what's it going to? As it goes left, what is it doing? It's going to negative infinity. All right, and so now I do a limit for my right. So now I have a limit as x approaches infinity of k of x because we named it now. And so what's it doing as it goes to the right? It's leveling off at 0. All right, cool. And so on this one's a little bit tricky. All right, and so what I like to do on this, because I know I don't need to do this, but I'm going to go a step further to help you out with your homework. Did this flip, first of all? It flipped, all right? And so a is definitely less than 0. Does everybody follow me? Because you see it flipped. And so think about it like not flipping. If it didn't flip, if you flip it back, it's there. Does everybody make sense of that? And so now what do you know about b? B's in between what? 0 and 1. And so b is in between 0 and 1. And so anyway, if you have to, try to figure out if a is greater than b or a is greater than 0 or less than 0, maybe flip it to like put it back. All right, so let's look at c now. So what do we know about a? What's my a on c? My a is 5, true that. Which is what? Greater than 0. All right. And then what's my b? It's in between 0 and 1. And so on these, I would draw a little sketch. And so what's it mean when a is greater than 0 and b is in between 0 and 1? It's going to go what? Down like that. All right. And so now if we look at our little picture, it's really simple. And so that's what I would do if it's written in a form just like the function form instead of the graph. All right. And so now when we do a left, we're going to say a limit as x approaches negative infinity of, does this one have a name? Yes. So we're going to call it g of x. And so when it goes left, which way does it go? Positive infinity. Good. All right. And then my right hand, I'm going to have a limit as x approaches positive infinity of g of x. And what does that go to? 0. All right, pretty good? All right, let's keep moving. All right, so example 2. So we need to figure out if it's increasing, decreasing, or concave up or concave down. And I'm going to go a little further after we kind of answer some of these questions because really these are pretty basic. So is A concave up or concave down? It's concave up. Is this increasing or decreasing? Decreasing. Now I want to talk about A and B. Okay, what's A? Positive or negative? It's positive, exactly. And what's B? It's in between 0 and 1. All right, I know it didn't ask for that, but I want you to get in the habit of doing it. All right, and so let's look at B. Is this concave up or concave down? It's concave down. Is this increasing or decreasing? It's decreasing. All right, and so what's A? It's less than 0. So on these, I kind of want you to think about hey, flip it back. And so if you reflect this thing over, it's kind of looking like that. Does Does everybody make sense of that? And so if it's looking like that, what do you know about b? It's greater than 1. Exactly. All right. Pretty good? All right, cool. All right, so let's look at C now. Does this one have a picture? No. So let's draw our picture. And so what do you know A is? It's greater than 0, right? And what's B? It's greater than 1. And so now I should be able to draw my little picture. And so what's my little picture going to do? Whoop, just like that. All right. And so now, is that concave up or concave down? Concave up. Is that increasing or decreasing? It's increasing. All right. Now, I want to go a step further on this one because it's going to help you out with number 14 on your homework. Where is it crossing my y-axis? So where does it cross my y-axis? At 3. Why is it at 3? Because that's the initial amount. Because the y-axis is called what? X equals 0. All right. If you were to substitute in 0 right there, you end up getting what? 4 to the power of 0, which is 1. 1 times 3 is 3. Fantastic. All right. Robert's going to read. Here we go. Example 3.
Selected values of the function f are shown in the table above. Determine if f could be linear, quadratic, exponential, or none of these.
All right. Beautiful. So let's look at our input values. So what do we know about our input values? 1, 6, 11, 16, 21. They're all going up by 5. And so they're equal inputs. All right. And so do I need to divide by 5 every time? No. All right. So Caroline, 3 to 5. What do we got? 2. How about 5 to 9?
4.
Yes.
8.
Yes.
16.
Yes. All right. So is it linear? No. All right. Because then my average rate of changes would be constant. Is it quadratic?
Yes. Or no?
No. Because is my second difference constant? No. Or my first difference is linear. So no, it's not quadratic either. So is it exponential?
Yes.
Yes, it is exponential. Because what's happening from 2 to 4 and 4 to 8 and 8 to 16? It's multiplying by 2. And so this is an exponential function, and I want to give a reason. All right. It's because the average rate of changes average rate of change, average rate of change starts with the P. Does anybody know it? Proportional. They're proportional. All right. So if you understand your A's and your B's of exponential functions, this is not too bad. All right.